General concepts of stochastic random processes. So first thing is that we have defined and learned a random variable which is a function of c, and these c is from your possible outcome of your experiment, and then you have a function x, and x of c is a real number. In contrast, a stochastic random process, instead of the output of this function be just a real number, is a function. So is going to be a function of time for a specific c. So this is a time function. Remember that the input of this function is one of the outcome of your experiment. For instance, for example, suppose that, and quite often we abbreviate and we don't write these c as we do the same thing for random variables. For instance, in this example, I write x of t as a stochastic process, which is equal to r cosine of omega t plus theta. Assume that these r and theta are two random variables. So these two guys are two functions of c. So therefore, x of t is a function of t and c and is a stochastic process, is a stochastic signal or a random process, because it has time variability and it also depends on the outcome of your experiment. Another example, suppose that c be a random number in the interval of 0, 1. Now, any number in the interval of 0, 1, you can have a binary representation. C is equal to this one. So generally, this is the formulas. Summation of, let's say, bi 2 to the power of minus I equal 1 to infinity. So any number in this interval has a unique representation. So C has a one-to-one relationship between the sequence of B1, B2, etc. and let's say Bn, etc. So if you determine this binary sequence, you uniquely determine this one, and if you know this real number between 0 1, you can determine this one. So there is a one-to-one relationship. So this binary representation, you could consider Bn is a function of n, and you can consider time or the location of the bit, and is also a function of c. So the nth bit is like a stochastic process. So a stochastic sequence or process. So when you have time here. So we need to define some nomenclature, and this nomenclature allows you to read scientific papers because they are common. We often abbreviate a stochastic process by this one. We don't usually write this one. We just say stochastic process. That means that it is random and there is an experiment and there is a probability space. There is a triplets. We don't need to talk about it. It is there. And if for any fixed t, if t is a real number, we call it continuous time, because t is in a continuous set. R is the set of real number is a continuous set. So it's a continuous time random process or a continuous time stochastic signal. If t is discrete, for instance, if you have done some sampling, in that case we call x of t as a discrete time stochastic signal or discrete time random process or discrete time noise. Noise, a stochastic process, random signal, these are same thing. For example, if you look at the values of these function, if these values are countable, then we call them discrete space. If x of t and c can take like binary values, if x of T and C is in this set of, let's say, 0, 1, then we call it a binary signal or discrete state process. Sometimes it could be 0, 1, let's say 5 volt or minus 5 volt, and let's say 12. In that case, this is discrete state because the value that x of t and c can take on is countable. For instance, in a DSP, in a digital signal processor, both time is discrete. We call it discrete time process because you have a clock cycle. Not only that, but also if you write any value, this value has a binary representation. So the values that x, let's say if it is 8-bit, then x can take 2 to the power 8 different values, and it is countable. Therefore, it is also discrete state process. Time also is discrete. We call it discrete state and discrete time process. So the state refers to the values that x can take, but when we say discrete time, these discrete time represent the values that t can take. If the value that t can take is countable, we call it discrete time. And if the value that x can take, we call it discrete state. A state refers to the value of x, and time refers to this index. So here, if I consider a fixed time here, then I will get a random variable for different values. Now, in contrast, if I take C1, then the randomness goes away. I will get a continuous time signal. C2 gives me another signal. So x of t and c, if you fix this one, this becomes a deterministic signal. If you fix t, these will become a random variable. So let's talk about this. So x of t is a family or an ensemble of time functions depending on c. That means that if c is fixed, this becomes a time signal. And if you fix c, this will become a time function. And if you fix t, this becomes a random variable. That means that if this is time, if you look at this, the value of your random process at time t, you get a random variable here, x at t. And if you take it at like t2, t1 and t2, you get x of t2, x of t2, you get 2 random variables, and so on. So different samples of your stochastic process, some time samples, are random variables. And x of t is a real number when both of them are fixed. So is a 2D function. One axis is time, the other axis is c. So because you remember that when we deal with lots of random variable, then equality requires a meaning. So you could have equality or convergence everywhere, convergence or equality mean square, or convergence almost everywhere, improbability, in distribution, L1, and so on. So all the concepts that we learned in other chapters, we can use them. If you take 2 samples, is 2 random variables, so you could use your knowledge in previous chapters. So most of the concept you have learned in previous chapter, you can use it here. Not only that, but almost all concepts you have already learned from the previous part of the course, and this part we are going to just exercise them in this context.